the 11th dimension of prime numbers. There are 11 possible places where you can find a prime number in modulo 30. The 2 and 3 and 5 in modulo 30, and 2 and 3 and 5 are prime numbers, but 32, 62, 92 aren't prime numbers. Other dimensions or line where you can find prime numbers are the lines of 7, 37, 67, 97. This is the class of 7, where you can find prime numbers. I studied the 31 class, which is the class with remainder equals to 1. It happens when you divide a number by 30. For instance, divide a cake in 31 slices, and now a group of 30 people show up and each one of them take a piece of cake. So now has left over one piece of cake. On the first line, you will find 11 prime numbers. They are 2, 3, 5, 7, 11, 13, 17, 19, 30, 29, 31. After that, we will see 8 lines from top to bottom. 2 to 31, first line, index 30 equals to 0. 902 to 931, last line, index equals to 30. This description is the Euler function of 30, where we can roughly count the prime numbers. Index 30 equals to number minus 2 divided by 30. Index equals to 0 means you are in the first line. It tells us the quantity of prime numbers approximately. The Gauss equation also tells us the quantity of prime numbers equals to n divided by logarithm of n. It is true because logarithm of n is the probability of finding a prime number until n. There is a race to find the missing primes, numbers that are generated by 2 at the power of n minus 1. If you find missing prime, you find a perfect prime too. Perfect prime that if you sum the divisor, you will end up seeing the number again. It's kinda tricky. What about the 52nd prime number? Lucky Durant found the missing prime using a hardware GPU to accelerate the computation. So look, speed up the race to find prime numbers. Other numbers similar to that are the Fermat's numbers. 2 of the power of 2 of the power of n minus 1. That is only 5. Why this? I believe there is some trick to prevent square plus 1 to generate prime numbers indefinitely, but I couldn't prove it right now. The RSA algorithm said that non-prime is the product of two numbers equals to 2 or greater than 2. Is not a prime number, and if you use two prime numbers, you hide them in a bigger number. That is the RSA algorithm because it is very hard to split two prime numbers from a big number using classical computer. Now the twin primes, they are numbers separated by a distance of 2. 5 and 7 are twin primes. That is the question. Are there infinite twin primes? We can look into classes 11, 30, and 17 and 19, and 29 and 31. I blend Euler of 30 and the binary code, where 7 is the lowest power equals to 1 and 31 is the highest power equals to 128. So I use don't care to 2, 3 and 5, and I use the set 7, 11, 13, 17, 19, 33, 29, and 31 to generate the binary code. And the 255 only happens in index 30 equals to 0. I believe to prove the last twin prime using the tag 71. That is 7, 11, 30, 39. At the same time, turning on. It's related to algebra 2 because we can make a table horizontally with 7, 11, 13, 29, and vertically 17, 19, 33, and 31. After that, we could use tag 254 or 223 or 222, where we have 3 twin primes together. It could force the last twin prime too. The problem is that when a tag has number rest 19 and number has 31, you will need all prime numbers to verify. Using tag 71, you will spend half of the time. It will use reminders 7, 11, 13, and 29. The question is the equation to find a non-prime below. 2 times k plus 3 plus 30 times j1 plus 2 times k plus 3 plus a plus 30 times j2 equals to 2 times b plus 1. Another equation, 2 times k plus 3 plus 30 times j plus 2 times k plus 3 plus a plus 30 times j plus 30 times l equals to 2 times b plus 1. I thought the next step would be 300, but if I wanna go beyond 30, the next step will be 210. But we will have to deal with 48 lines.